All right. Whenever you're ready, take it away.
Okay, can you see my screen here?
Yes.
Wonderful. Just gonna turn my camera off, just while I at least talk. Okay, I'm guessing you can still hear me. Hi everyone, my name is Troy. I'm from the Harvard-Smithsonian Center for Astrophysics, and today I'm going to share a funded program by NASA, the HTM program on modernizing XRT-Pi with a Python-based DEM solver. This work is in collaboration with Dr. Reeves, Dr. Weber, and Dr. Murphy, who are also here at the CFA. So first, I just want to talk to you about Hinode and the XRT instrument. It was launched in 2006, nearly coming up to 19 years of observations. XRT still remains the only operational solar X-ray imager of its kind. It observes a plasma between 1 to 10 million Kelvin, and it is essential for studying coronal heating, flares, CMEs, and jets. If you look at the image on your right, this is a full disk image taken by XRT in the AO mesh filter. As you can see hot coronal plasma while also seeing cool regions on the surface of the disk, on the disk. And if you look at the top right, that is an illustration of the Hinode spacecraft, and that black linear tube at the bottom, that there is the XRT instruments. So XRT has a unique filter wheel combination, one in front of another, and through this you can arrange different filters to give you a different temperature range of observations, which pretty much gives you a unique coverage of, it gives you unique thermal coverage of the corona. I want to show you this quick movie that was done using Python. You yourself can download XRT data, look through it, and even make a movie, and it's available on our documentation site, which I'll share at the end. What we're looking at is a coronal mass ejection near the limb as the sun rotates away from us. I'll show it to you one more time. It's beautiful. So what is XRT-Pi? It's a Python package for Hinode XRT data. So in short, we implement the legacy IDEO SolarSoft tools and transform them into Python open source in a reproducible way. We are fully documented. We give you a full general information about XRT and XRT-Pi, methods of getting started. We have a series of example galleries in Python that you can download or just follow and do science yourself, contributor guide, and much more. To share some of our current capabilities, we have what we call channels, which is the instrument configuration and metadata. For example, if you want to know more about the filter, you want to know more about the filters, the kind of coding, the thicknesses, that sort of information, or even the CCD camera, and get information on that. You can get that through channels. We do effective area calculations, temperature response, imaging processing, plasma diagnostics, and a few more. We're actively developing, and like I said, a lot of these things that we offer are originally in IDEO and translated over to Python. To give you one example of our modules, here we have temperature response fundamentals. This gives you the temperature response calculations. Here's one of the plots that you can do with XRT-Pi, which is all of XRT's filters plotted with the Chianti abundance coronal hybrid and photospheric near the launch date. So now that you know about XRT and what XRT-Pi, I just would quickly want to highlight there's some challenges when we talk about DEMs. The first one is that DEM analysis is still locked into IDEO, which limits I always get this word, it's a tongue twister for me. You can replicate. It's limited. I mean, it's limited to. Okay. In short, it's locked into IDEO and it's not easy to access. It creates a barrier for new researchers and cross-instrument science. The wonderful opportunity is that we can bring DEMs into Python, integrated with XRT-Pi, and ensure that it aligns with PyHC and some Pi standards, making these crucial diagnostic tools open and interpretable. So you've been hearing me say DEMs. What is that? Well, DEM stands for differential emission measures. It tells you how much plasma is present at each temperature in the sun's corona along your line of sight. Each XRT filter, the ones I highlighted at the beginning of this presentation, has a unique temperature response. And by combining these, you can reconstruct the temperature distribution of plasma. So DMs are crucial for understanding coronal heating processes, flares, and coronal structures. So multi-filter data gives you stronger diagnostics. The more filters you have in your data, in your observations, the better your differential emission measure is. To give you one short example, here's an image taken on July 10th of 2007, and there is one active region on the left side of the disk. That's active region 10963. If you zoom into that flare, here's an image taken by XRT in the AO poly filter. If you can see the crosshair where my cursor is, you can get the intensity straight from the XRT data. And with that, we can understand the amount of plasma being ejected, the amount of plasma temperature diagnostics at this crosshair at that intensity. And here it is. Here's an example of that. So on the x-axis, you have your logarithmic temperature scale. And the y-axis, you have your emission measure. It tells you how much plasma is present at each temperature. So the two things I like to draw your attention to is the green curve. That is the DM derived from the observed intensities, and the black dotted line, which is the Monte Carlo trials, shows you the uncertainty in the solutions. To talk a little bit more about the complexity of DEMs, this is the equation that you can get your DEM from. You have your observed intensity, sort of like I showed you before. You have an observation, you pick a pixel, and you can get the observed intensity divided by the exposure time, which is how you get the data numbers per second, integrated over the temperature response, which is already offered in XRT Pi, times your differential emission measure, integrated over temperature. As simple as it sounds, you would just get the DM on one side and get all the other values on the other side. But there is some complexity with this. Mathematically, it's ill-posed, meaning you'll get different solutions every time you calculate the DEM. One thing to notice is that it's sensitive to calibration, noise, abundances, and many other assumptions. So to get the best differential emission measure out of your calculation, it requires iterative filling and error estimation. In this case, Monte Carlo runs. So I want to now talk about what this new DEM solver will look like in XRT Pi in a Pythonic version. We're creating this class called XRT DEM iterative. Iterative is a keyword. It tells you the method of which the DEM is being calculated. Here's currently what we see what it will look like is the following. The three things I want to draw your attention to is the observed channels, observed intensities, and the temperature response. You know your filters, you have your intensities that you're interested in, and you have the response. Like I mentioned, you can calculate this in XRT Pi. The rest are default values that you can tinker with or adjust to try to get the best output for your DEM calculation. This is exactly what is mirrored in IDEA, and we're transferring to a Pythonic version. To quickly highlight something new, at responses, we created a new tool recently called Generate Temperature Response. You give it your filters, an observation date, and your preferred abundance. And it'll nicely format it in a way that it fits into the class, the DEM class. Yep. So now that you know about about XRT, XRT Pi, and a little bit about what DEM is and what we hope to look like, I want to talk about this grant itself, as described by NASA. It stands for this grant is the Heliophysics Tools and Methods, which funds the development and maintenance of open source Python software and analyzes methods that supports heliophysics missions, data interpolation, and community-wide scientific discovery. So our plan to get this DM to follow with the project views is to convert the ideal solver into Python. That current ideal solver is called XRT DM iterative 2. And we're just going to transfer that into a Pythonic version by re-implementing modern libraries such as NumPy, SciPy, LMFit, AstroPy, Matplotlib, and much more. Next, we want to integrate this into XRTPy. It'll be open source, documented, tested, and we'll have several Python example notebooks on how to work with this DM. We'll make sure to validate this with both synthetic and real data sets and mirror it to IDEO. And last is to interpolate, connect with SumPy, SunKit DEMs, so that it's interpretability with other instruments and missions such as STO AIA. And the way we plan to do that is we're community-driven development via GitHub. This is our roadmap to follow with the HTM program. And I just want to highlight that this directly supports PyHC's mission, which is improving reproducibility, lowering the barrier for students and new researchers, and building sustainable, shareable heliophysics ecosystem. So by aligning with PyHC and SumPy standards, the solver becomes not just a tool for XRT, but it also strengthens the community as a whole. And last, I would like to just give you current status on our solver. We're currently in the process of building it. Next, we'll be doing integration, testing, validation, and documenting. We're hoping to release this in XRTPy version 0.6, and that'll be in the spring of 2026. To give you a roadmap, I'm highlighting where we are today and where we're heading for, or aiming for this DM release, which will be the spring of 2026. I would just like to comment that feedback and contributions are welcome to XRTPy, not just with this DEM solver that we're creating, but in all our other works. So I'd like to just say thank you on this grant that we're hoping to start. This project we're hoping to start through this funding grant very soon. Here's my contact info if you'd like to get in contact with me. I invite you to visit our GitHub site so you can see our current projects, and you can scan the QR code below to check out our documentation site. Thank you.
Thanks, Joy.
Yeah.
Does anyone have any questions or comments or thoughts?
Yeah, I want to start with a quick one.
Sure.
Towards the end there, during your future work, you were describing some of the packages you'll be using for the next upcoming IDL transition, writing it over to Python. And I'm just wondering, when you were making the initial version of XRTPy, did you use any PyHC packages or any higher level things, or did you just use plain Python to translate the IDL?
Everything that we started with and that currently exists was all strictly just mirroring IDL, and we were able to just use basic Python libraries that are currently existing. So we haven't yet used any PyHC tools yet.
Nice.
So we're hoping this will definitely be the right time for this. And we will be working with SumPy on integrating this, because this is a wonderful tool, not just for XRT, but different instruments and missions as well.
Yeah, I hope it makes the translation easier, not more complex.
Right.
All right.
Okay.
Any other questions for Joy?
Thank you.
All right. Thanks again, Joy. All right, Brian, you are up.
Hey, everybody. I wish I had gone first because I don't have nearly as many cool images and stuff. All right, so let's see. Let me share my screen. Okay, wait. Is this the right screen? Okay.
We see slides.
Okay, cool. Yeah, and thanks everybody for bearing with me. I was sick last week, 2 weeks ago, rather. Monday was like the peak of my sickness. It was crazy. I was asleep during this conference. So
No worries.
all right, let's see. I'll just do it in this mode if that's all right.
Sure.
Yeah, let's see. Okay, there we go. Yeah, so the title of my proposal was called Sustaining and Enhancing CDF-lib, a Python first common data format library for the heliophysics community. So basically, in a nutshell, it's supporting the library CDF-lib for the next 3 years, but I'll go more into some more detail on the next slides. So I'm Brian Harder. I'm from the University of Colorado, Laboratory for Atmospheric and Space Physics. The co-I on this proposal is Brent Smith from Hopkins, APL. I don't know if he's on the call. No, he doesn't appear to be. But I know he's active in the PyHC community. So what is CDF-lib? Just a little background for those that don't know. It's an open source pure Python library for reading in the common data format or CDF files. And the advantage of CDF-lib over other CDF writers is that there's no external dependencies. There's no libraries like C or Fortran. So it's just easy installation with pip install CDF-lib. So it broadly works with a lot of different platforms. And it's pretty small and just pure Python code. So what's it have? It has reading and writing CDF files. There's a epochs module for converting between the different CDF time types, or CDF time types and Unix time, or CDF time and AstroPy time. It's just for working with times from CDF files. And then in addition, there was a 2020 Roses proposal, which we won, that allowed CDF-lib to integrate with Xarray. So there's now these functions that convert Xarray data sets to CDF files and vice versa. So where is it used? Well, CDF format, I mean, I'm pretty sure we're all familiar with it. It's used for tons of different heliophysics missions. And currently CDF-lib is a dependency of PySpeedas, and I've seen it used in SunPy, but primarily it's the backend CDF reader for PySpeedas. It's also used in mission data pipelines for different heliophysics missions. Of note is IMAP, which is currently in development and is going to launch in like 2 weeks. And then I've seen ESA use it as well for their Vera's mission, or Swarm. I don't know how to pronounce it, but yeah, so it's pretty widely used. And in fact, in the proposal, I cited one of Sean's papers that showed a list of the different libraries that heliophysics researchers have installed, and CDF-lib was up there. I don't remember the exact number, but it was on most of people's machines. Very brief history of CDF-lib. It started out from the Maven Science Data Center. There was some funding that the data center had for data visualization, and we wanted to use a Python library to do it. And to do that, we needed to read in the Maven CDF files. So it started off as just like a pure Python CDF reader, me combing through the internal format description documents from the CDF library, and figuring out how to read them in just with Python. But eventually it grew, and now it can read, write, and do all these different cool things. In 2020, it was awarded a grant for the Xarray integration, which I talked about previously. And then over the last like 5-ish years or so, as it's gained in popularity, David Stansby, just a shout out to him. He's provided a lot of crucial voluntary support to CDF-lib, and so has SciVision. That's their GitHub handle, and I completely am spacing on their name right now. But he's probably contributed to some of the other Python heliophysics projects. They've been contributors. And then IMAP adopted CDF-lib, and I'm on the IMAP mission, so I got some funds from the Science Data Center to help integrate the CDF-lib into their processing pipelines and fix any bugs that they find. And then today, IMAP SDC funding, that's pretty much dried up. The mission, like I said, is launching in a couple weeks. And there's no mission in the pipeline at last to continue CDF development. So there was kind of a need for additional funding to support the next few years of CDF-lib. So what we're doing, we have this HTM grant to support CDF-lib for the next 3 years. And our goal is to make sure that CDF-lib remains a reliable, accessible, and well-supported tool for the heliophysics community. And this is critical to provide support for the entire community and not just single missions, which is kind of where the focus was before. Initially it was Maven, and then over the last few years when I've been working on CDF-lib, it's really been just things that impact IMAP, and anything else that I get as a GitHub ticket has kind of been on the back burner. Okay, so these were the key project goals outlined in the proposal. One is to ensure that CDF-lib remains compatible with the latest CDF versions. There's new CDF versions that come out periodically. ISTP standards, which is a standard format you put your CDF file in. Those also have been evolving. So just making sure that we keep up to date with those. Addressing community needs. Like I said, I've been getting GitHub tickets. CDF-lib has been getting GitHub tickets. And there's currently, at least as the time of the proposal, there's 38 open issues, which I have prioritized in various ways. But there's definitely a lot of need for support here. And then improving robustness. So right now, our unit tests cover about 73%, and we'd like to bump that a little bit higher. Just as a goal for this proposal, we want it to be over 90%. And then improved maintainability. The Epochs time conversion modules, a lot of that was really directly lifted from the C code, and it's a little bit hard to understand and not very well commented. So I made a special shout out to refactor that complex code for increased maintainability. And then Brent Smith from APL's role in the project will be expanding CDF-lib's accessibility using FS spec. And he recently won an HTM award either last year or 2 years ago to do FS spec with various other PyHC projects. So he may have worked on some of your projects, I'm not sure. And what this basically does is it allows those projects, and it'll allow CDF to read and write files from cloud storage just as easily as local files. So you can have the CDF file sitting on S3 or on Google Cloud, or it can be on a different server, and FS spec will handle it. Very rough timeline. Year 1, Brent Smith is going to complete his FS spec integration, and we'll also be increasing test coverage. Year 2, we're going to really focus on implementing the high priority community feature requests. Year 3, we're going to work on refactoring the Epochs module and all the documentation that would come along with that, and enhancing the documentation in general. And then throughout all these, through these years, any critical bugs that show up in the GitHub issues, we'll be responding to those, and any new versions of CDF or ISTP, we'll be monitoring those and making sure that those are implemented in CDF-lib as well. And I think that's it. So there's a link to CDF-lib. We have a project board for, this is where we kind of keep track of, what tickets are, what priority there is, and if anybody's working on them. And yeah, that's about it. Oh, I asked Google AI in slides to make me an image of whatever it thought CDF-lib was about. So I pasted that in because I thought it was funny. It's like CDF-lib, CDF-lib, CDF-lib. Like, okay. Any questions?
I don't have a question, but I appreciate this AI generated impression of CDF lib.
Yeah, I had never seen it before. It popped up while I was doing this, and it's like, "Do you want to make an image?" I'm like, "Maybe." So,
Fair enough.
Hi, Brian.
Yeah.
This is Joy. And
hello.
so I work with the Parker Solar Probe mission, specifically the sweep instrument, and I'm starting a new project. I'm trying to create some Python pipeline work, having to do with some data. And I was tasked to work with CDF files, so I'm really happy to see this. And just last Friday, I did a pip install of CDFs. So I'm
Mhm.
going to use this. I'm going to use this package. So I'm really happy to know that there's efforts in this, and that it'll continue to to only get better as the code that I write is supposed to last for the rest of the year, not till the end of the mission. So thank you for
Okay.
doing this, and I'll definitely be active on your GitHub if I have any suggestions or need any help of any kind. But so thank you.
All right, fantastic. Yeah, that's great to hear.
Yeah, no questions yet, but I'll be
Okay.
using this package literally after this meeting. That's on
Okay,
my
cool.
task.
That's awesome. Okay, cool.
Yeah. Actually, kind of on that topic, just you pointed out during your talk that CDF lib is becoming kind of a fundamental package for a few different things. I'm wondering if you could just speak for a second to like how stable your like API has been over the years, and like if this upcoming work, if you're planning on like maybe releasing a version 2 or making any other big breaking changes.
My goal wasn't to release a version 2 or make any sort of breaking API changes. The API has pretty much remained stable. The one thing that I was maybe considering doing is trying to see what I could do with the X-ray to CDF portion and have it maybe work with other CDF readers in the community, since that's the CDF to X-ray portion is not very dependent on whatever the backend is. It makes like 2 calls basically to a CDF writer or CDF reader thing. So it barely depends on it. So that was one thing I was considering doing. But other than that, the interface I was planning on keeping pretty much the same.
Well, right on. That's easy for everyone.
Yeah.
Yeah, I just want to give a shout out from PySpeedas. It's been really helpful to us to all the work you've done on CDF lib, and it's solid. Thank you very much. Very reliable.
Oh, great, thanks.
Yeah, I'll give me another shout out. I contributed to an S3 patch, not as good as FSS spec, but it's a really easy project to contribute to. So, if we're looking at the PyHC projects and having a process for contributing, theirs was pretty good to do as an outsider. So if people want to contribute, consider it.
Oh, yeah, thanks for that plug. Except for the Epox module. That's why I want to reformat it. That one's a little bit opaque, but
Any other thoughts, comments, congratulatory remarks? All right. Thanks so much, Brian.
yeah, no problem.
Yeah, and congrats to both of you and our previous presenters on getting these HTM grants, especially in these trying times. All right. Well, unless someone has a walk-on topic or something they specifically want to chat about, we can go ahead and call this an early ending. I'll give it 3 seconds of silence. All right, it's a wrap. Thanks so much, everyone. See you again
Bye,
in
everyone.
2 weeks. Same idea.
Sounds great.
I had a quick question.
Sure.
I noticed you mentioned that you guys were able to find out who won the grants. And I mean, I recently found out maybe like right around the same time you told me, more or less. Do you know where I
Right.
can find that information?
Oh, So usually that's on the NASA Roses site, I would
Okay.
think. I just knew the person funding them. So
Right.
I asked him, hey, can you send me a list if we got funded so I can start talking to people? But yeah, apart from that, I think it would just be on the Roses site. You might have to dig a little.
Okay, no problem.
Yeah.
Yeah. Okay, wonderful. Yeah, I'll definitely start attending more often as part of the mission is to contribute to PyHC and see how we can come together. So thank you.
Good thing.
Great.
Thanks.
Bye-bye.
All right. Shut the recording off.